A cup of coffee, a hot iron rod, a freshly baked pie, they all cool down. But how fast? Newton's law of cooling gives us the answer. Here's a hot object at 200 degrees, sitting in a room at 10 degrees. Heat always flows from hot to cold, so energy leaves the object. The key insight is this: the bigger the temperature gap, the faster it cools. As the object cools and the gap shrinks, the cooling slows right down. We can write that idea as one clean equation. The rate the temperature changes, dt by dt, equals minus k, times the gap between the object and its surroundings. The k is just a constant that depends on the object and its environment. And that minus sign? It's what makes the object cool instead of heat up. To find the temperature at any time, we solve the equation. First we separate the variables, temperature on one side, time on the other. Then we integrate both sides. That gives us a natural log, and when we undo it with the exponential, the temperature difference shrinks like e to the minus kt. Finally, we use the starting temperature to pin down the constant. And here it is, the cooling formula. Temperature equals the surroundings, plus the starting gap, times e to the minus kt. Plug in our numbers, 10, 200, and k of 0.1. And we get T equals 10 plus 190, e to the minus 0.1 t. Now watch it happen. The curve drops steeply at first. That big 200-degree gap means rapid cooling. But look how it bends. As the temperature falls, the curve flattens out. It glides toward the dashed line at 10 degrees, and gets ever closer. But never quite touches it. That's the signature shape of exponential decay. Let's put it to work. What's the temperature after 10 minutes? Substitute T equals 10, the exponent becomes minus 1. E to the minus 1 is about 0.37. So the object has cooled from 200 all the way down to about 80. So, to recap, cooling speed depends on the temperature gap. That idea becomes a simple differential equation. And its solution is an exponential decay toward the surroundings. The object races to cool when it's hot, eases off as it nears the room, and approaches 10 degrees forever without ever truly arriving. That's Newton's law of cooling.